some of the topics that some of you have been learning in physics or had learned.
Can y'all hear? Can
Yes.
pick up our voice?
Yeah, it picks up your voice.
Ollie. Hi, Ollie.
There you go. Hi, Ollie. Okay. All right.
You should get an intro like Miss Malikian.
Oh my God.
I heard about that. Okay, and instantaneous rate of change. Instantaneous rate of change is the same thing as derivative. Yes, we've already done it, but we're going to actually apply it in terms of, we'll see shortly with velocity, acceleration, so on. Instantaneous rate of change is the derivative. Okay. Now I put in here, provided the limit exists, and that's because I said everything we do in calculus is based on limits. So when we're doing this, just keep in mind, we're not going to do the definition here. Don't worry. We're going to do all of our shortcuts, but just a reminder that it goes back to that formal definition. Okay, enlarging circles. So we're going to pretend there's a circle and it's getting bigger, okay? We want to find the rate of change. So we want to find the rate of change of the area with respect to its radius r. Okay, so first thing I want you to do is let's write the area of a circle as a function of r. So meaning I want
A equals pi r squared.
Okay, so I want a of r, and yes, equals pi r squared.
Am I supposed to do that?
Yes, absolutely. Pi r squared. You definitely need to know pi r squared.
Is pi r squared or 2 pi r?
There you go.
2 pi r or
Okay, so here we go. So imagine that as the radius is getting bigger, the actual area of the circle is also getting bigger, right? It's also increasing. So we want to find a prime of r. So we're going to move the 2 to the front. So 2 pi r to the first power. 2 pi r. Not a coincidence, okay? What we'll discover is a lot of times when we do the derivative, like the derivative of volume is going to give us surface area for solids and things like that. We'll actually see that correlation here in calculus. Okay, now we want to evaluate the rate of change of A at r equals 5 and when r equals 10. And we don't have to plug this into our calculator. We'll just leave it in terms of pi. So plugging in 5 will give us 2 pi times 5, which is... Oh yeah, we're plugging it into the derivative because we're asking specifically for the rate of change. Oh yeah, sorry, did I forget my little prime? Thank you. There, that's important. So 2 pi times 10 is 20 pi. So the larger the radius, the larger the rate of change of the area, which makes sense, right? As expanding. Okay, now let's talk units. Units are really important in calculus. So if r is measured in inches and a is measured in square inches, what do you think dAdr? Now dAdr is just another way to say a prime of r. So I had mentioned this is your Leibniz notation, this is your Newton, just be used to both of them. What are the units? So it's going to be square inches per inch. Now, we don't cancel the square with the inch because these are different units. This is a square inch, and this is a linear inch. Okay, so this means what? You can't cancel them. Yeah, you like simply, it's saying for each square inch per linear inch, that's how much the circle is expanding. Okay?
Wait, how do we know that those are the units?
It says it. A is measured in square inches. Radius is measured in, so if it's DADR, we're going to do square inches. Now, if you want to put it over, like square inches over inches, it's the same thing. It doesn't matter to me.
No. You wish.
Okay, here we go. Motion along a line. Okay, so we are going to talk about particle motion or objects in motion. So when we have the position function, okay, remember that the position is always going to be a function of time. So our position, we use x of t. Usually it could be just f of t. X is just the name of the function. Usually if we have particle motion, we say it moves along an x-axis, so it's like moving back and forth. Displacement. Okay, well, displacement has to be what?
Like from something.
The distance from where it started from, okay? So you have a time interval from T1 to T2, so we're going to take basically your end position minus your starting position. Now, keep in mind, you can move things in a positive or negative direction. So, for example, if I say you start from home, you drive to school, and then you drive back home, your displacement would be 0 because you started and ended at the same place. Okay? So your displacement could be 0 if you start and end in the same place. Yeah.
Every day is 0, even though I'm like school.
Yeah, so we're going to talk about the difference between total distance traveled versus your displacement. So if you live 10 miles from school, right, you start from home, you drive 10 miles to school, and then you drive home 10 miles. Your displacement is 0, but the total distance traveled would be 20 miles. Okay, so we'll talk about that also. Okay, average velocity. Average velocity is displacement over time. Okay, this is your f of b minus f of a over b minus a. This is the same thing as your slope of your secant line. Okay, average rate of change, average velocity, we've already done. Okay, good so far? Nothing surprising here. Instantaneous velocity, that is our first derivative. Okay, so just like I had just mentioned, instantaneous rate of change, instantaneous velocity. It is the derivative of the position function always. Always with respect to time. Okay. Speed. Okay, speed is the absolute value of velocity. So whatever our velocity can be positive or negative. Good.
Wait, but it's absolute value of like not the instantaneous,
Just the last stage.
because it
Not
says
the
that it's
derivative.
v of t, not v prime.
No, it's just v of t.
Okay.
Wait, but speed is velocity.
Oh, speed. Yeah, speed is the.
Speed is the absolute value of velocity. Okay, take for example, you take a ball, you throw it up in the air. Okay. Well, throwing up, so when the ball goes up versus coming down, one's going to have a positive velocity, one's going to have a negative velocity. But if you clock the speed, right, you would always say it's positive. That's why your speedometer, right, it's always going to have a positive miles per hour.
Okay, so it's the absolute value of the
Whatever your
derivative.
velocity is. Yeah, the derivative. It's absolute value of whatever your velocity is.
So the instantaneous.
So velocity, so just a quick note here. So velocity can be positive or negative. Okay, it's totally allowed to have a positive or negative velocity, whereas your speed is always positive. Okay, 2 more concepts and then we'll go through some examples. Acceleration is the instantaneous change in velocity. Oops. So this is the derivative of velocity, again, with respect to time. So acceleration is the derivative of velocity, or the second derivative of the position function. Okay. And just a note on the units for these. Let me just go back real quickly. Position is not so important to put units, because usually you just get like, you would say like 3 units to the right of where we started. Velocity, average velocity, and instantaneous velocity will always be, these will always be like a linear unit. Yeah, per unit of time. Right? So for example, meters per second. So same thing for instantaneous. So velocity, average velocity, this is always a linear unit. Miles per hour, feet per minute, meters per second. So same for speed. These are all, I should just write this. This is all the units for this and this as well. Acceleration is going to be a linear unit per unit of time per unit of time.
Oh, so it's
So
meters per second squared.
So it's a linear unit per unit of time per unit of time, because you are differentiating twice with respect to time. Okay. Some of you will say square seconds. There's no such thing as a square second. It's per second, but it's okay to use the two. So I could use an example like meters. You could write meters per second. That's fine. You could do meters per second with an exponent too. Just know this is simply notation. There's no such thing as a square second. That makes no sense. Okay. All right, speeding up versus slowing down. So when velocity and acceleration have the same sign, your object is speeding up. Versus when velocity and acceleration have opposite signs, it is slowing down. Think about throwing that ball up in the air. Right? As you throw the ball up, we know gravity is what? Is negative. So your ball, as you throw it up, it's slowing down. So you have a positive velocity, right? Negative acceleration. So your ball's slowing down until it hits that maximum height. And then what happens when it starts going back down to the ground? It's correct. So we have negative velocity, negative acceleration. It is speeding up towards the ground. Okay, good. And now we look at our examples. Okay, here we go. We got a dynamite blast propels a heavy rock straight up at a launch velocity of 160 feet per second. Okay, so that's about 109 miles per hour. We don't need to really know that because we're going to just keep it in feet per second. Reaches a height. So x of t is what? This is our position function, right? If it says launch velocity, that's what? Well, that's our initial velocity. A launch velocity, okay? But for right now, let's just focus on, here's our position function. Okay, so here's the blast, right? It's going to hit this. We want to figure out how high does the rock go? Okay. When is it going to reach its maximum height?
No, that's the lowest.
A v equals 0.
Ah. when v of t equals 0, right? When the velocity equals 0, because remember when that rock goes up in the air, right at the moment where it hits that maximum height, it's got this instant where it stopped, where its velocity is 0. So I got my position function. What do I want to find? I want to find the derivative to find velocity. So let's go ahead and find velocity. Again, we're using all our shortcuts now. We don't have to worry about any of that.
60 minus 32t.
Good. 160 minus 32t. We are going to set that equal to 0 and solve for t. 5 seconds. Now, I still didn't answer the question, but I kind of asked a second question, right, after that first one. So when does it reach that maximum height? At 5 seconds. Now we plug it back into x of t. So exactly. So we're going to plug into x of 5. So that's going to be 160 minus 5 minus 16 times 5 squared. So 800 minus 400 feet. Just feet, right? That's going to be how high. So position is just going to be regular linear units. Okay, so far, good. All right.
Velocity and speed, same thing.
So speed is the absolute value of velocity. They have the same numerical value, but velocity can be positive or negative. Speed can only be positive. Okay? So what is the velocity and the speed of the rock when it's 256 feet above the ground on the way up and on the way down? So here, like look at our little, I know that's really small. So on the way up, it's going to have a negative velocity. So it's going up. So it's going to have positive velocity, negative acceleration.
Negative acceleration.
There you go. So positive velocity here, coming back down, is going to have a negative velocity. However, the speed's going to just be positive. So first thing I want to do, it says specifically when it is 256 feet above the ground. Okay. Well, I need to figure out when that occurs.
T equals 7. They have to plug it into the original equation.
No, but it's not time.
Set it equal to the, okay. So I need to find out when is x of t equal to 256, right? So you have to think about, I'm working in terms of time, but I'm giving you the position, so I have to kind of work backwards, okay? So we're going to have to figure out when is the position equal to 256. Now I should get two values because it said there was a time where it's going up and a time where it's going down. So let's take a look. Here's 256, 160t minus 16t squared. Save some time. Everything is divisible by 16, right? Mm-hmm. 256 is 16 times 16. I'm going to move everything to one side and divide by 16. We're okay with that all at once, yeah. Okay? So t squared minus 10t plus 16 equals 0. And yes, I gave you numbers that factor nicely. Okay, so both should be negative. If you end up with a positive number, we ignore that value, okay? Because you can't have a negative time. But it makes sense that we have two values that work here. So at t equals 2 and 8 seconds. Okay, now, so which one is on the way up? 2. Okay, so on the way up, v of 2, oops. So we'll go back up here because we did find the velocity. So 160 minus 32 times 2, so 160 minus 64.
96.
And that makes the speed the same. I'm going to do 2. I'm going to do 8 next. So this was, so if you notice, that's why I labeled on the way up.
But is it on the way up?
Well, okay, so the thing is here with this picture, this original function has really nice symmetry to it. So at 2 and at 8 seconds, I'm actually going to get the same numerical value, just positive versus negative for velocity. So on the way down,
So just like really find it and then like go all the way up.
yeah, so now we just want to do, I mean, hopefully it makes sense why I said the first one was going up and the second one was going down versus, but yeah, and obviously if you plug one in, you're going to get a positive answer and the other one is going to be negative. So it's got a positive velocity, negative velocity, plugging in 8.
Why is T up?
What's that?
Why is T up and 8 down? 2 up.
2 is going up. So, okay, so here's T equals 0. So as it goes up, at T equals 2, it's going to hit 256 feet. Keep going up until it reaches its maximum height. And then it starts coming. Now remember, this was 5 seconds.
It's also slower on the way up than it is on the way down.
When you say,
Like
Your
the speed at which you're throwing, like,
well, the speed's going to be the same.
no, on the way up and down.
Well, yeah, because when we plug in 8, we should get negative 96 feet per second, which makes the speed the same. Okay, so again, let's kind of think about what that means in the context of the problem. So it's starting off from the ground, right? It's going to go up at 2 seconds. It's reaching 256 feet at 96 feet per second.
Oh, and then it goes up.
Then
6
it
more
keep
seconds.
goes,
Or
yeah,
like
it goes up 3 more seconds to reach a maximum height of 400. Right? Wasn't that what it was?
Yeah.
And then it starts falling back down. Here, it now has a negative velocity of negative 6 feet per second.
It's like it's taking a lap. Like
It's
coming
back, yeah. However, the speed is always just going to be positive. So it's going just as fast in terms of speed.
But how do you know that 2 is up and 8 is down?
Because you start on
Really, just
one
like
and
plug it in first. This is 2.
it becomes positive.
When it goes up,
And then
you start on the bottom.
it reaches top and then it comes back down. So it has to be.
okay, just a quick reminder, if velocity is going upward,
The direction is positive.
so it's greater than 0 when something is going up. Velocity is going to be less than 0 when it goes down.
And it's also the direction.
I know I get
Yeah. Okay, I'm going to move on. What's the acceleration of the rock anytime?
It's it would be 32. Oh yeah.
Yeah. Negative 32.
Oh yeah.
Yeah.
Okay, how do we get that?
So this was our velocity function. What's the derivative of that?
Oh.
That number should look familiar. If we were measuring in meters per second, it would be negative 9.8 meters per second.
Can we also write the v double prime effect?
Sure. I just wanted to label it. So yeah, this is the derivative of the velocity function. So again, just using the power rule. And those of us in physics or just in general, our gravity is always negative. Okay, when does the rock hit the ground? So this is going to be when x of t equals 0. It's hitting the ground, right? Okay, because we're a little short on time, I'm going to, so we're going to go back to the original. And I can factor out a 16t. So when t equals 0 and 10 seconds. Now, I asked
10 seconds.
specifically when does it hit the ground? Well, it makes sense that I got 0 and 10 because 10 was our starting point, right? So it's going to take 10 seconds. Also, yeah. So if you recall from the first question, we found out it reached a maximum height at 5 seconds. Since this graph has symmetry to it, it makes sense that it's going to take 10 seconds. Cool. All right, what do we have on this one? Oof, yeah, okay. Woo.
15.
I think we took a longer time on homework than I was expecting. So, okay. I'm thinking maybe, you know what? Let's skip to the next page. Only because that middle page, I can easily do that in like two minutes. I just want to explain in terms of the graph. So here's particle motion. This is called the s-axis, sometimes the x-axis, it doesn't matter. So you have a particle moving back and forth. Okay, this is what it looks like, graphed position. So if I'm asking you, when is the particle moving to the left and moving to the right versus standing still, what am I looking at on that graph? Yeah.
So if it's standing still, then it's just going to be like a constant
Yep.
slope. The slope is going to be 0.
Slopes. Yeah, so we're looking at slope. So standing still will be where it is a horizontal, okay? Where it's moving to the left, it's going to have a negative slope. Negative slope. So, okay, so where is it have a negative slope? 2 to 3, 5 to 6. Good. Let's use parentheses here because when it stopped, we'll use just at value. So this will be from 2 to 3 and 5 to 6. Has a positive slope, just 0 to 1. And it stopped at 1 to 2. Oh, yeah. Let me put brackets. Or 1 to 2. What did we say? 3 to 5? Good.
Oh, when were you going to
I was going to put it at a point, but I forget it. Okay. How would we graph the particle's velocity and speed? We've done this before. Remember, this is going to be where we look at the actual values.
Wait, but is this like with 2? Like the speed ones, it always has to be above the, like.
Correct. Okay, so let's see here. From 0 to 1, we have a slope of 2. So I have a horizontal line here. From 1 to 2, it's at 0. From 2 to 3, it has a negative 4 slope.
Wait, no. Why would 1 to 2? Oh, 1 to 2 is 0, yeah.
And then we have another horizontal from 3 to 5. And from 5 to 6, it has a slope of negative 2. Now, when we graph the speed, anything that's below the x-axis just gets reflected above the x-axis. If it's already above the x-axis or on, we leave it there. So this is going to stay the same. This is going to stay the same. This one's going to stay the same. So the part that goes from 2 to 3 is going to get shifted up from negative 4 to positive 4. And the part that goes from 5 to 6 that's at negative 2 will just get reflected up to positive 2. Yeah, if I asked you to graph the acceleration, yeah, what are the slopes of all the velocity parts? Yeah. Okay, so this screencast. So, well, this is just. So at 29 minutes, if you want to fast forward to 25 minutes.
Oh my god, I'm actually sure. Can I sign up for 2 at the same time? Wait, how can you do that?
I'm leaving.
Okay, thank you.
All right, you're welcome. So displacement is just x of 2 minus x of 0. So you're just plugging
I'm
in
good,
here.
Okay.
Okay.
I'll do it.
Average velocity
Yeah. Well, I mean, it's like best to go to as many as you can.
is
You never know.
going to be x of 2 minus x of, oh, sorry, 4.
Sorry, Miss Kate.
No, that's okay.
Are we gonna be where do you want me to go for the test? Or
Oh,
quiz?
when were we taking it?
B.
Oh, you can come here. I actually have a class that's taking a test anyway that period.
Oh, okay.
It's in my 9th grade classes.
Isn't it X prime or?
No, because it's average velocity.
Yeah,
Okay.
but isn't the equation of
No,
position? Oh, that's for average velocity.
average. Yeah, average. The next one is the derivative. Okay.
Wait, so you can get the average velocity if we're still using the speed equation?
I know. That's fine. You can come in.
Or the position equation?
Well, we're just finishing up. So 3 minus 3 over 4. So that's 0 meters per second.
What? 6 over 4?
No, x of 4. X of 4 would be 16 minus 16 plus 3 is 3. Minus x of 0, which is 3. So 3 minus 3 is 0.
Oh.
Yeah, that's okay.
Oh, I remember that's.
Okay, instantaneous velocity is going to be the derivative. So first thing I'm going to do is find the derivative. So that's going to be 2t minus 4 from t squared minus 4t plus 3. And now I'm going to plug in 4. And I'm going to get 4 meters per second. And then,
Wouldn't it be the acceleration?
no, so v of t is x prime of t. So v already implies that you're taking the derivative. Okay, acceleration is going to be v prime of t. So that's just going to be 2 meters per second per second. And then the last thing, really easy peasy, velocity is 2t minus 4. So if I do a quick number line, so when t equals 2, my velocity is 0. So that's when the particle is going to be stopped. Okay? If I pick a value between 0 and 2, say 1, I'm going to end up with a negative velocity. And then if I pick anything bigger than 2, I'm going to end up with a positive velocity. So, yeah, it's going to change direction. At t equals 2. And it is moving left from 0 to 2, and it's moving right from 2 to infinity. Oh, positive versus negative. So anytime it's a negative, it's moving left. If it's moving positive, it's moving right.